We are glad that we have here Federico Vincentelli for this weekly seminar. Federico actually has a postdoc in Instituto Astrofisico de Canarias in Tenerife, where he's working on multi-wavelength path variability of accreting neutron stars. He takes his degree here in Rome, La Sapienza, and the degree thesis has been made in Osservatorio Astronomico di Monteporzio with Pier Giorgio Casella on X-ray and infrared timing in black hole transients. Then he moved for his PhD in Como, but he worked also with Tommaso Belloni in Merate, and then he had a postdoc in Southampton for 3 years, working on AGN with McCarty. And in 2021, he came back to working in X-ray binaries with a postdoc in Villanova University. And then he moved to Canarias. Today, he will speak about the accretion instability of black hole and neutron star. That is a nice work that is published in Nature this year.
Thank you very much for the kind introduction, and thank you very much for inviting me here in my home city. It's a real pleasure to present this work that I've been working the last couple of years, and I finished while working with Joint Institute in Villanova. So as Fiamma said, very briefly, in this work, we confirmed a fundamental prediction of accretion disk theory, which is that when an accretion disk reaches high accretion rate, we have an unstable process which happens independently on the nature of the central object which is accreting to this accretion disk. In order to bring everybody at the same place, therefore, I will first give an introduction on what is a low-mass X-ray binary, which are the objects that we studied in this work. And then I will explain what I mean when I talk about an accretion instability. And then I will, of course, present you our results. So let's get started. What is a low-mass X-ray binary? A low-mass X-ray binary is a system which contains a compact object, so a stellar mass black hole or a neutron star. Sorry, I need the timer so I don't lose track of time. So it contains a compact object, so a stellar mass black hole or a neutron star, and that is accreting from a low mass star, so a mass of a star of roughly 1 solar mass, through the formation of an accretion disk. These systems are very interesting because they allow us to study the accretion phenomenon with high statistics, because they are very luminous, as they are in they're very bright because they are in our galaxy, and also they have a lot of advantages. First of all, they are transient and recurrent. So what does this mean? These systems spend most of their time in quiescence, so low luminosity below the detection threshold of our telescopes, and show brief periods of activity that we call outbursts that can last few weeks to months or years, where they have an increase in accretion, a very big excursion in accretion rate and luminosity. And this is which means that we can study the properties of accretion at different accretion rates, which is something that we cannot do with many other systems. Moreover, these outbursts are recurrent, as you can see here from these X-ray light curves on functional days. And therefore, we can do this over and over again over different outbursts, and of course, also different systems, because we have, let's say, tens of these systems in our galaxy. Moreover, these systems are very interesting because they have a very broad spectral energy distribution. They, as you can see here from this SCB, which spans almost 10 orders of magnitude in frequency, and this is telling us that there are multiple components acting at the same time, and actually they vary significantly and sometimes dramatically during this outburst, which means that we can study in detail all the components involved in accretion and therefore understand what happens in the innermost regions of these systems. Therefore, given that there are these multiple components, in order to fully understand the phenomenology of these systems, and therefore also this instability I will show you later, we have to first introduce which are these main actors, let's say, these components. after decades of multi-wavelength observations at different times, different wavelengths at different times, we have identified mainly four emitting components. So the first one is, of course, the main engine, which I said before, is the accretion disk. Accretion disk can reach a very high temperature as the system as it reaches close to the object, and it meets in therefore can emit X-rays. The spectrum of the disk can change a lot during this outburst, and sometimes we have a thermal emission coming from a geometrically thick, but we also have sometimes a non-thermal component from a puffed disk, which is optically thin. I won't go into detail on what is the geometry exactly of the accretion disk because it's really still highly debated. I just want to make the point here that this geometry can change as a function of time, and it can also change quite fast. Another very interesting properties of accretion disks and of the accretion flow is actually that it's very variable. If we go and look at short time scales, the luminosity is a function of time, we can see, as you can see here, that this is just a 5-second snapshot, and we have very strong periodic variability, which are, let's say, fluctuations in the accretion disk. And this property is very important because it gives us a key to understand better the geometry of the accretion flow. So the accretion disk, as I said, very hot in the inner part, but can be say it's colder in the outer part, and so it can emit also optical infrared wavelength. But the inner part of the accretion disk can also irradiates actually the outer part of the disk and also the donor star, and therefore this irradiation component can also play a significant role in the SCD and in the spectral energy distribution. But we also see it when we study the variability of this system. So this is an example where we have, for example, a very strong X-ray flash from the innermost part of the system, in the top panel here. This is a type 1 X-ray burst, so an explosion on a neutron star. And we see how the disk and the star has a smooth and delayed response as an echo from the inner part to the outer part. And this can be used also to map, let's say, the orbital parameters of the system. I will show you an example later on. As we go at lower wavelength, we also start to see other components. So the high energy part is dominated by the disk, but if we go at lower energies, we start to see other components. So we can see, as I said, the other part of the disk, but we also see jets. So these jets are collimated outflows where matter is accelerated up to like a fraction of the speed of light. So they're very powerful. And as matter is accelerated along these collimated outflows, it emits synchrotron radiation, which can, and its emission can go from optical infrared to radio. And after, say, decades of observations of low mass X-ray binaries, we now know that there are two flavors of jets. We have some kind of discrete ejection, some blobs that we can actually see them with VLBI observations move away from the system. So this is a multi-epoch image where we see these blobs going away from the system. But we also see, we can see very well that as these blobs expand as a function of time, their frequency, the synchrotron peak frequency evolves, say, cools down. And so from this red curve, which is the infrared, it becomes this green curve here in radio. Along with these very powerful events, we also have, let's say, jets can also be, let's say, can be a more continuous flow. And in that case, instead of like these discrete blobs, we will, with let's say a very discontinuous spectral energy distribution, we will have a flat spectral energy distribution because the jet will be filled. And you can see, and therefore we see a flat spectrum from radio to optical infrared wavelength. Along with these very collimated and strong outflows, however, in the last years, we are starting to see also another flavor of outflow, which are, let's say, called winds. So these are, let's say, less collimated and less powerful jets, less powerful outflows, so which are called usually winds. And we see them as blue shifted absorption lines in highly inclined systems. So this is because the matter is being launched towards our line of sight, and therefore this light is absorbed, and so we see this blue shifted absorption line. And we see this not only in X-rays, so we see not only in optical UV, but also in X-rays, which is telling us, therefore, that most probably there is a multi-phase outburst outflow, as sometimes seen in AGN as well. So as you can imagine, all these components are, let's say, have some kind of interplay between each other. So, for instance, the presence of the jet or this outflow can change the geometry of the accretion flow, and as well, and also the other way around, depending on the geometry of the accretion flow, we can have jets or not. And so it's important, therefore, to understand actually the physics of all these components, and Loma 6 binaries are really great example of how we can use all these components to extract physical information on the accretion process. And as I will show you today, the moment where we see this at its best, where all these connections are really strong, is when we have high luminosity and we have this kind of instability. So therefore, now that I explained to you all these, I introduced you these actors, which will be important for our study, I will now pass and explain to you what I mean when I talk about accretion instability. So, as I told you, the main engine of accretion of Loma 6 binaries is the accretion disk. The main model which can explain this accretion disk, which has been invoked, is the so-called Seminari disk, which is a optically thick, geometrically thin disk, which emits thermal emission with a multicolor black body. As we go closer to the central object, we have a higher temperature. And this model has been proven in many times with many objects. This is an example, for instance, that when we have a black hole that is fully dominated by the accretion disk, we expect the luminosity to scale as a fourth temperature, as a fourth power of the temperature if the area is constant, and we see that this is very well, this system is very well behaved. So the theory is actually works very well also for other systems at many different masses. However, this solution has a problem, because this has been shown from the 70s that this model is actually unstable, which means that when we have high luminosity, so roughly 10% of Eddington, the radiation pressure of the disk becomes stronger than the gas pressure, which means that if you have an increase in accretion rate, the density will collapse. This can be seen quite well if we do a accretion rate versus surface density plot. And this gives origin, so the fact that the radiation pressure dominates over the gas pressure will generate this S sigma or this S curve, which, as I said, means that as we go from this branch towards higher accretion rate, the density will collapse. And then it has been proven then that if you go higher luminosity, we reach another stable branch. So this is a problem for the theory, and this is actually even a bigger puzzle when we go and look at observations, because there is one system or maybe two systems that show this kind of behavior. The most famous one, which has been studied also many people in this institute, is the famous JS15+105, which, if we look at the X-ray light curve, shows a very peculiar pattern. So if we look here, what we are seeing in this X-ray light curve, that when the system reaches a certain threshold of luminosity, these dramatic oscillations on very short timescales start to appear. And these oscillations are also associated to strong variation in the spectral hardness, so which means of the spectral energy distribution of the system. And this has been already from observation. This was, let's say, a proof that the disk was changing dramatically its structure, but also from theoretical studies, it has been shown, semi-analytical models, it has been shown that these oscillations can be explained with the system going through the S branch here. So this is temperature versus density. But as the system goes through the S branch, the disk is changing its morphology. So these are here on the right, there is the radial density profile, and you can see that as the system goes through the S branch, you have the disk going up and down in the part of the disk. So as the system is going in the S branch, we have a cyclic disruption and rebuilding of the disk on very short time scales. So this is really, this system was is really unique in its kind. There's only one maybe other system that shows this kind of oscillations. And apart from that, so as I said, this is really a unique system because the only maybe no, it's not unique. So there is this system and maybe one other system that shows let's say systematically these oscillations. But apart from that, we don't have many of them. So for instance, this is an example of two sources that are two neutron stars that are, one is a normal, say, kind of atoll high luminosity neutron star, and then a ULX that showed in one observation by chance, without a particular moment in their life, this kind of patterns. And this is, and so it is a problem. So is this the same thing? What right there is this kind of oscillations? Is it the same process? And also the bigger problem is that we expect way more systems to show these instabilities. Because, as I said, we expect an unstable process when we reach 10% of that luminosity, but we know many systems that reach this threshold. So we should need, we expect way more. And we don't see them. And as I will show you later, our study seems to gives an indication of this, an indication of where these problems, these systems can hide. As a next step, there's also another solution that we can think of to try to solve this problem is to go and look at other high energy systems with multivariate observations. But the problem is that the multivariate variability of high activity system is really complex. This is an example of the famous B404 Sydney, where we have radio light curve, infrared, optical, and X-ray light curve bands. And you can see that the variability is very complex. And so it's very complicated to try to disentangle what are the components here. So on one side, we expect way more systems, and we don't know where they are. On the other hand, the few systems that we know that have really high accretion rate show a very complicated variability. And so it's very complicated to study them. And for both these problems, our study indicates a way to solve this problem. So now that I gave you, let's say, I gave you a review of accretion stability and what are the problems of this regarding this physical process, I can now go and explain to you how we kind of solve these problems with our study. And the system that we studied in particular is SwiftJ 1858.6 or minus 014, 1858 for friends. And this system is a transient neutron star, which went in outburst in 2018. And this is the nicer light curve of its whole life. And you can see already by eye that there are two main patterns here. So in the first year and a half of its life, it showed a very flaring behavior, where you can see here on the right, let's say recurrent flares on 107 timescales that are almost 2 orders of magnitude in amplitude. And these systems also, this system showed a partial, a strong obscurer. The spectrum needed a partial coloring absorber. and the inferred luminosity was quite high, 10 to the 37 nanometer per second. And in this state, these systems also showed strong outflows at all wavelengths, X-ray, UV, and optical. In the second part of its life, the system showed what actually it is. So we didn't see any more this partial obscurer, but we started to see type 1 X-ray bursts, which is telling us, as I said before, that the system is a neutron star. Moreover, more importantly, this system started to show eclipses, which means it's a smoking gun of the fact that the system is edge on. So we are seeing a neutron star, which is almost edge on, and the orbital motion gives these eclipses. Thanks to a very big collaboration, we managed to put up an impressive monitoring campaign to observe this system during its flaring state. And this campaign involved many different telescopes, and this is just a part of the campaign. So we had NuSTAR. So this is the campaign dedicated to the extreme variability. And we managed to observe simultaneously in 5 bands. So with NuSTAR for the X-rays, UV, HST for the UV, Liverpool telescope with for the optical, Hawkeye at the VLT in the infrared, and VLA for the radio band. And you can see already by that there's a really strong flaring behavior, which is not very common in X-ray binaries. So just to show you a zoom inside here, you can see that there are recurrent patterns on 100 times, on 107 timescales, and which are very big across and are very big, and they seem to change its amplitude change as a function of wavelength. And so the question like I had, but plus we also have very short flares here say 1 second duration. And so once we got these light curves in 2019, I had a big question, which is how do you explain this multivariate variability? This is not normal, so we don't see these very strong flares, especially at all these wavelengths. So from Southampton, I moved to the US, and I started working on this project with Joy, and we focused especially on the infrared band because it's the one that's best sampled because it has very high time resolution, 0.1 second time resolution, and doesn't have as many gaps as the other systems, as the other wavelengths. And after playing with the data, removing, let's say, the short variability, we realized this. We found this, which is telling us that the infrared light curve of a neutron star, or a acrylic neutron star, is very similar to the X-ray light curve of a black hole. So the blue light curve is JRS 1915, obtained by Chandra, which is already kind of mind-blowing if you think about it. And therefore, I continued, and therefore we tried to investigate how can we make this happen, because this is not something, it's like something really unexpected. And after working on different hypotheses, we realized that the most reasonable one is that there must be the same physical process taking place in both systems. So we must have the same instability taking place in 1915 and in 1858. And the reason why we see the seed in infrared for 1858 is because it's easily explained if we assume that there is irradiation from the other part of the system. And the reason why we don't see it in X-rays is because the system is edge on, and so it's partially obscured. Of course, we cannot, let's say, stop here and cannot stop here and just say this is quite really similar and therefore must be the hypothesis. We have to actually test it properly. So we did several tests, and the first test was to actually prove that, or confirm that this can be consistent with being reprocessing. So if it is eternal reprocessing, we have a weapon to use, because if it is reprocessing, then there will be a delay between the X-ray emitting region and the outer part of the system, because the light will take time to go to the outer part and then be re-emitted. So what we did is to go and get all the simultaneous bits between X-ray and infrared light curve and measure the lag for each of these systems, for each of these segments, sorry. We know that the system is eclipsing, so we know we have an idea of the orbital period, and we can compute the orbital phase. So what we did is to plot the lag as a function of orbital phase, and you already can see that the lag is very big. It's like a few seconds, and it's evolving as a function of the orbital phase, which is promising. what we did, therefore, as a next step, is to model if these lags could be consistent with the orbital motion of a system with the parameters of 1858. So we developed a model together with Yuri Kavecki. This was also from another study, where we can compute the expected lags from the processing of a binary system for a given orbital period and inclination, and mass ratio, etc. And we applied to this data. So we fixed the orbital period and the mass, and using the mass ratio given by the eclipses properties. And we found that for an inclination of 80 degrees, more or less, we have a really good agreement between our model and the data, which is telling us, therefore, that the infrared light curve is fully consistent with being reprocessing of the other part of the accretion disk on a light curve that looks like 1915. So the first test is actually say, passed quite well. So luckily, 1915 has been studied in many different ways and say almost to a pathological level. So we have many things that we can actually test further to be sure that this is actually what is happening, that we are really seeing the same thing. And we did two main tests here. So the first test is regarding the fast variability. So these heartbeats. And the test is the following. So 1915, during these heartbeats, has a spectral evolution. And from space result spectroscopy, we know that at the peak of these heartbeats, we have a strong evidence that there is non-thermal X-ray emission at the peak of the heartbeat. Can we see the same thing in 1858? So, well, we have some candidates, which are these very short flares here. These are too intense and too short to be thermal emission. So what we did is to stack them all together and see if there was some connection between these flares and the long-term behavior. And we found, with quite big surprise, that these short flares take place, this is the stack of all the flares. These short flares take place exactly at the peak of the process heartbeat. So we are seeing, again, the same thing. So these short flares are let's say, direct evidence of the non-thermal flaring that we see in 1915. So again, we can explain this phenomenology with the same scenario. The other test, which I think is even the more important, probably the most important, is the radio part. So 1915 is a very strong radiometer, and these ejecta I showed you at the beginning of the talk were taken by 1915. 1915 was the first object to show superaluminum motion in our galaxy. So let's say we have to, so if we have this kind of behavior in 1915, we also have it in 1858. Moreover, more importantly, 1915 has in infrared a very strong contribution from the jet. But in our case, we have it from the process emission. So if we are invoking the same physical process, we have to explain why in 1915 we see the jet in infrared, in 1858 we see reprocessing. So what we did is to go and get archival data. This is a campaign that Joey did many years ago, where we had radio observation, time zone observations with Chandra, simultaneous with Chandra, and we modeled this light curve and our light curve with a model that involves multiple ejecta, as we know 1915 does. This is a model that was done by Alex Starenko to see if we could see this, the model can explain both systems with the same, let's say, more or less parameters. So this is the application to the fit or to the radio light curves. And so the blue and red curves are the, let's say, multiple components of the ejecta. And you can see that in both cases, the radio light curves are very well explained. And the very interesting thing is that if, with this model, we can go and trace back when the ejection are taking place. And if we go and compare them with the, say, driving light curve, so the X-ray light curve for 1915, and the infrared light curve for 1858, we see that this ejection time take more or less place at the transition between the flaring and non-flaring state. So between the stable, unstable, and stable phase. And So this is really interesting because it's telling, and this thing has been seen also in other, like before there is also a similar scenario. So we're actually seeing that's really confirming that there is same thing going on. But the final test is the infrared, because as I told you, we have to explain why we don't see it in infrared, we don't see the jet in infrared for 1858. If we go and scale the radioluminosity of 1858 to the infrared using the same scaling relation that we observed for 1915, we actually find that the infrared contribution is lower than the jet contribution, which means that invoking this same scenario does not break the processing model. And therefore, if we take a step back, this is telling us something really, really important. It's telling us that the X-ray instability that we saw in 1915 can actually be seen in other wavelengths depending on the property of the system. So if we have this instability process, depending on the inclination or the jet contribution, we can see it more in X-rays or in infrared. For instance, in 1915, we have access to the inner part of the system, so we see the instabilities very well. But when we see in the infrared, the jet is so strong, it's so powerful that it dominates the reprocessing component. 1858, we are actually at the opposite. We don't have access to the inner part of the system because it's edge-on, and it has outflows, it has obscuration, but we see its effect on the other part of the system. Moreover, the system is a neutron star, so the jets are not as strong, and so the jets are lower than the reprocessing contribution. And moreover, let's say this is telling us that with simply three ingredients, which are accretion instability, reprocessing obscuration, and jets, we can now explain the complex motivated variability of low mass X-ray binaries when reaching high luminosity, which, as I told you at the beginning, is a puzzle. So it's very complicated. So we can now go back to, let's say, these multivariate, impressive multivariate campaigns on V404 or also other systems and try to disentangle this complicated variability and extract physical information from the system, which otherwise cannot be obtained. And moreover, this scenario is giving us, let's say, a new framework with which we can study new outbursts of highly accreting systems. So now, in the last part of the talk, so now I explained to you how we can, let's say, explain the multi-wavelength puzzle. And in the last part of the talk, I now explain to you the other puzzle, which is where are the systems that show this kind of instability. So in order to answer this question, we have to put the 1858 in the context of other neutron stars. So after, say, further studies of this system compared the radio and X-ray properties of 1858 and showed, for example, in this radio versus X-ray luminosity diagram, that 1858 is consistent with a highly accreting neutron star. So consistent with what we are saying, and in particular, is consistent with being a Z source. So it's a low luminosity Z source. Z sources are thought to be highly accreting neutron star systems. But therefore, this is important because this is telling us that 1858 is indicating us that Z sources are possible sources of this kind of instability. And we can now go and check the phenomenology of Z sources to try to understand where the stability is taking place. So luckily, this kind of system have been studied many times, and especially by Rob Fender with Simone Migliari, Terminus Darius, and Sana Motta. And we have a very clear, let's say, phenomenological picture of these systems. So we know that these systems, when they go through different states, show strong ejecta. And in particular, I won't go too much into detail because it's really a bit boring and complicated. But what we know is that when the system goes from a, let's say, from a certain state to a so-called flaring branch, so a very variable state, as the name says, we have an ejection. And this is actually what we see as well in the T58. We know that we have an ejection when we go from a non-flaring to a flaring state. Therefore, this is telling us that when we go to the so-called normal and flaring branch, we have this instability. So as also, this was suggested by Fender's work, but they couldn't pin it down. But our work really shows that the same accretion instability that is taking place in 1915 is happening in the flaring branch. And therefore, this is very important because now we can go back to Z sources, which are highly accreting systems and are very bright and persistent. So we can go observe them whenever we want. We don't have to wait for a new outburst. And they are to go and study this instability. And moreover, they are also very bright in optical, in the infrared band. So we can go and do a multi-wavelength study of these systems and understand better the origin of this instability, which of course, is not fully understood yet. And moreover, by studying, let's say, neutron stars, we can compare that. We can compare this instability with so we can compare the instability of these neutron stars with the instability that we observe in black holes, and try to understand what is the contribution of, let's say, of a black hole or a neutron star to the jet launch mechanism. Moreover, we can, for instance, we know that we can see really from the plots I showed you that these oscillations have a very different timescale depending on the system. And we don't know why this is happening. Is it because is it only the region where this is happening? Is the magnetic field taking place? Does it depend on the magnetation of the disk? Does it depend on the truncation of the disk? Does it depend on the jet efficiency? We don't know. So by going and studying Z sources, we can actually go and answer to these questions, which are open and very interesting, especially for theorists, because let's say this instability is very fully understood from a theoretical point of view and is not confirmed by numerical simulations. So it's really a very nice project that we can actually go and study. Moreover, we can actually go and study this with X-ray polarimetry, because as of course many people of this group of this room know, most of the sources that have been detected with X-ray are neutron stars. And we know that there is some kind of evolution between the different states. And we know that in results that show that as we go from different branches of the Z source, we have an evolution of the polarimetry, so of the X-ray polarimetry behavior. So we can go, we will need a lot of collecting area, but we can go and study. So with X-ray polarization, which is very strong constraint on the geometry, we can understand how the geometry evolves during this instability and therefore understand better its physical process. These are my conclusions. So I showed you that a neutron star system, Swift J58, shows in infrared the same instability that has been observed in X-rays for the black hole 1915. I showed you that thanks to this discovery, we could put up together a new multi-wave framework with which we can explain the let's say the multivariate complex light curve of highly accreting systems. And I showed you that thanks to this discovery, we now know that Z sources are the, say, missing sources that show this instability, which were expected from theory. This discovery opens very interesting new roads, because thanks to this, we can go back to past material light campaigns, but also do new observations to study better the nature of this instability. And also we can, what I'm doing now actually is to develop a model to link, let's say, this instability to the multivariate light curve and extract physical information from these systems. So thank you very much.